All right, everybody always says that it's their great pleasure to introduce someone, but in my case, it really is a great pleasure because Jerry's a nice guy. Can't say that for everybody. Jerry recently received the ACL's Lifetime Achievement Award, and that's basically why we're gathered here. He's made seminal contributions to computational linguistics for many years. His first well-known paper was in 1976, in which he gave an algorithm for pronoun resolution, and that paper is still cited until today. He's made contributions to other computational linguistics areas with colleagues at SRI, where he was working at the time. He designed and built FASTIS, which was the first lightweight information extraction system based on finite state technology, and that's a system that was imitated by many other people. Other early work he did around the same time with colleagues at SRI was the Tacitus system that implemented another one of his early and seminal contributions, interpretation as weighted abduction. This was an ambitious framework that was supposed to encompass all of discourse processing. He didn't only do work many, many years ago. He's done work over the years until today. He's made other contributions to semantics and syntax. His work on metaphor started early and stretches from the 1980s until now, where he heads a large IARPA-funded project on a metaphor. He's also done work in common sense psychology that stretches from the 1970s until today. So I think you get a sense, even from my introduction, of why the ACL decided to give him a Lifetime Achievement Award. He'll reprise for us now the acceptance speech that he gave at the ACL a couple months ago when he received this. So there's a reception that follows, so don't go away. And it's my pleasure to let Jerry talk now.
So if I really wanted to duplicate the event at the conference, what I would have done is hide behind the curtain, and then as soon as he all said my name, I would jump out like a jack in the box. I learned about this award last March, but you're not supposed to tell anybody until it's actually announced at the conference in August. And Priscilla Rasmussen, who's the power behind the throne at ACL, insisted that it be kept secret right up to the moment that it was announced. And so she had me hide behind a screen in the hall and then kind of step out when my name was mentioned. I want to start with a show and tell. So this is the trophy. I think it looks rather nice. The part about it I like the best is that it has my name on it. I think that's its most aesthetic feature. So I naturally, in the talk, I started off by talking about how honored I was to get the award. I mean, I was especially honored when I look back at the list of previous winners, people like Chuck Fillmore, Eugene Charniak, Fred Jelnick, Martin K., Aravind Joshi, and the others. They're all my heroes. And of course, I was delighted to learn of the award. The most we can hope for in life is to take part in the conversation. And an award like this means that you've taken part in the conversation. So it's a tradition in these awards to begin with a few formative anecdotes from childhood. Actually, for me, it all begins before I was born. My grandfather was a crusty old country lawyer from southern Indiana. He told my dad not even to bother to go to law school because he'd flunk out. He didn't know English grammar. So my dad went out and bought a book entitled English Grammar by Smith, Magee, and Stewart, 1928, and mastered the book and went on to become a very successful lawyer. So fast forward to when I was in junior high school, my dad was distressed that the English classes I was taking didn't cover any grammar, didn't seem to. And so he convinced me, persuaded me, actually probably bribed me, I don't remember what with, to master this same book. This was a concession on my part because I was a math nerd at the time. I was reading textbooks on trigonometry and calculus as my way of avoiding the humiliation of going out and playing baseball. But I read the book and I was amazed. English grammar was just like math. It had all the same abstractions, the same puzzles, the same systematicity. It was actually fun. So that was the kind of the first incident. I grew up in South Bend, Indiana, and Notre Dame University was nearby, and I hung out from about my sophomore year in high school on, and at the math department at Notre Dame University, and including hanging out in the reference library. And one day I found a book called Introduction to Descriptive Linguistics by Henry Gleason. And I sat down and read the first chapter on phonology, and I thought it was really fascinating. I mean, to think that there was mathematical systematicity to the sound system of English was really a fascination. But I never followed that up at all. And I've often wondered what would have happened if instead of picking up that book, I'd picked up Noam Chomsky's Syntactic Structures, which came out about that year. Would I have gained 15 years in my career if I had done that? In my junior or senior year in high school, we had to take something called the Cooter Preference Test. It would help us decide which career to choose. And I scored very high in language and in math. So my high school counselor said I should write math books. In fact, she got it exactly the opposite. It wasn't that I should do language about math. It was that I should do math about language. I've heard any number of computational linguists tell similar stories. They grew up not knowing whether they wanted to be a physicist or a poet. They just knew they both sounded fascinating. And then they discovered computational linguistics. So my last near miss happened with the week I was drafted into the Army. They gave us a battery of aptitude tests to see which specialties we'd be best for. One of the tests was to see if we should be sent to the Monterey Language School. And looking back on it now, I see that what they were testing was how well you could understand formal language theory. I mean, they would give you the rules for an artificial language and then give you supposed sentences in that language, and you were supposed to say whether they were correct or not. And I'd never seen anything like it, but I thought it was really fun to do. And a couple days later, I met with a personnel specialist who went over my test scores. And I could see that on that language test, I got 46 out of 50. And he was ignoring that. And I pointed it out to him, and he said, "Oh, that's a mistake. Nobody ever gets more than 6 or 7 points on that." I said, no, I think it might be correct. And he said, "It doesn't matter. You're not going to Monterey Language School. You're going to South Vietnam." Well, as it happened, I didn't go to Monterey Language School, and I didn't go to South Vietnam. I spent 2 years in South Carolina, and I was happy to be there. How I managed that is a story for another occasion. So I didn't really discover computational linguistics until my third year in graduate school at New York University. In October, I passed my oral exam in topics like algebraic topology and complex analysis by one generous pass and 2 abstentions. In the subsequent months, I discovered more and more facts about myself. For example, that I was never going to figure out a faster way of multiplying matrices. And that, fascinating though recursion theory might be, I was never going to prove a theorem that Hartley-Rogers would have to include in his next edition. As I surveyed vaguely plausible fields, I realized I had no idea what the next problem to solve would be, or even what made a problem interesting. So then in April, when I nearly resigned myself to becoming a taxi driver, I discovered New York University's best-kept secret, Naomi Sager's linguistic string project. I think it's also computational linguistics' best-kept secret. She was motivated by the science, not by the performance, and her very impressive work is nowhere near as well known as it should be. I think her linguistic string grammar ranks as a computational specification of English syntax with Pollard and Sogg's head-driven phrase structure grammar for thoroughness, insight, and elegance. So, for example, in 1992, when we developed the fastest system for information extraction using cascaded finite state transducers, it was straightforward to copy the rules for noun groups straight from her grammar. It's no accident in the late 1980s during the Strategic Computing Initiative, in the early 1990s during the MUC Message Understanding Conference evaluations, that three of the most important efforts were led by Linguistic String Project alumni, Ralph Grishman's group at New York University, Lynette Hirschman's at Unisys, and my group at SRI International. I think the most important lesson I learned from Naomi Sager was to look closely at the data and to take it seriously. My other thesis advisor was the mathematician Jack Schwartz. He was a polymath, so to speak. I took a course in logic from him. I knew about his book on compilers and the classic Dunford and Schwartz on functional analysis. But when I saw his book on mathematical economics and his book on the theory of relativity, I did some research to see if there was more than one Jack Schwartz. Among his writings was an unpublished Chapter 9 of his compilers book on parsing natural language, which of course I read. My thesis was on Early's algorithm applied to natural language. It quickly became apparent that the constraints on phrase structure rules had to be expressed, and that one could do that with fairly simple operations on vectors of features, where among the features were what I called the cores of the constituents, since they bundled many of the relevant features. My core was what linguists came to call head. Years later, I ran across Chapter 9 again and reread it, and realized that all the ideas in my thesis were there. So when in 1987, Schwartz told someone that I had anticipated head-driven phrase structure grammar, that was his way of saying that he had anticipated head-driven phrase structure grammar. My first job at Yale University was as a very temporary instructor. I think the position is now called postdoc. Over the course of the year, I became convinced that syntax was a solved problem, something I still believe. But that left me with a drift for problems to work on. I became discouraged and found myself thinking again about driving that taxi. Then late one afternoon, just as I was about to go home, a graduate student named Fred Howard came into my office to ask a couple of questions. They triggered a discussion that lasted until 11 o'clock that evening. One of the wheels we reinvented that evening was recognition of the pervasiveness of spatial metaphor in discourse. This was before Lakoff and Johnson, but after similar observations by the 18th century Italian philosopher Giambattista Vico and the 20th century English literary critic I.A. Richards. But within a year, everything else of value that remained of the conversation of that discussion could be compressed into a long footnote in a technical report. In any case, that conversation lit a fire that fueled my research for the next 15 or 20 years. In particular, I began looking at texts, trying to understand how we understand them. no doubt influenced by Chuck Rieger's thesis. I asked what inferences we draw in the course of comprehension, and an issue Rieger did not address, what inferences we do not draw. This culminated in 1976 in an unreadable and largely unread technical report, my last show and tell here, in which I microanalyzed one paragraph from Newsweek, trying to specify every bit of knowledge that's required for understanding that paragraph and describing how every linguistic problem in the text invokes that knowledge to arrive at solutions. One could say that the rest of my career has been a matter of cleaning up and extending that technical report in terms of representation, the processes of inference and interpretation, and the specification of common sense knowledge. In 1977, I moved to SRI, where I fell under the influence of Nils Nilsson and Bob Moore, and of John McCarthy at nearby Stanford. They were campaigning to replace the ad hoc styles of representation of early AI with representations based on first-order logic. But the problem in a nutshell is this. When we see a sentence like, Pat believes Chris is tall, we really want to write, believe Pat, tall of Chris. The trouble is that tall of Chris is a predicate applied to an argument, and a predicate applied to an argument evaluates to true or false. So you end up with Pat believed a truth value with no hint of Chris's tallness, no hint of the content of the belief. So the typical way of dealing with this in linguistic semantics has been to treat believe not as an ordinary predicate, but as some special kind of operator that blocks evaluation of its second argument. And numerous other kinds of modal operators are treated in a very similar way, possibility and temporal operators and so on. And logics have been developed for these. So we could just kind of adopt all of these specialized logics. And if we wanted to represent a sentence like, maybe the boy wanted to build a boat slowly, it would look something like this. We'd have Russell's iota operator to represent the definite article the. We'd have the nouns represented by types. We'd have special operators like modal operators like want. We'd use the modal operator possible to mean maybe. Past would be, the past tense would be represented by a temporal operator past. You'd have lambda expressions for kind of open expressions like the infinitive verb phrases. Adverbs would be functionals operating on predicates and so on. So it gets very complicated very quickly. And what bothered me about this was we're talking here about 15 or 20 words, like maybe and want and slowly. And are we really, if this is the kind of complexity we have to have in order to represent, these 15 or 20 words, what's going to happen when we have to represent 2,000 words or 20,000 or 80,000 words? Are we going to have 80,000 different logics to represent these things? It seemed to me instead we should abide by two principles. One, all morphemes are created equal, so that we shouldn't treat maybe and boat and past tense in any different way. Yes?
I hate to be a moron, but what's a morpheme?
Okay, a morpheme you can think of as a word. It's kind of the smallest meaning carrying element in a sentence. But it's really more than just a word, or less than just a word. So wanted is two morphemes, the want and the past tense. All right.
Thank you.
But you can, in general, think of it as a word. And secondly, every morpheme conveys a predication. So if we can get away with abiding by these principles if we apply reification, that is this is from the Latin word re, meaning thing, making things out of anything we can talk about. So in this approach, tall of Chris still says that Chris is tall. So now tall prime E Chris says that E is the eventuality or the state of Chris's being tall. And now if we want to represent Pat believes that Chris is tall, then we can say that Pat believes E, and E is Chris's, the property or the state of Chris's tallness. So when we do that, then the representation of the sentence, maybe the boy wanted to build a boat slowly, becomes this. Now it looks fairly complicated, but in fact the syntax is just first order logic. It's just predicates applied to existentially quantified variables with the widest possible scope, ranging over a universe of possible individuals. So we don't have to introduce all these exotic operators. It's just predicates applied to arguments. Now, this principle of one predication per morpheme can be seen in the extreme with this word the. I mean, I have the X3, E3 as that second proposition there. What in the world does that mean? Well, you have to ask, what is the information conveyed by the word the? And essentially what it does is convey a relationship between the thing referred to by the noun phrase and the property expressed by the rest of the noun phrase. So the boy, what the conveys is a relationship between the boy that's being referred to and the property of being a boy. And what it says about this is that X3 is uniquely mutually identifiable in context by the speaker and hearer by virtue of the property E3, the property of being a boy. Now we could kind of pack all this into a predicate that we could call uniquely mutually identifiable in context by speaker and hearer by virtue of property, X3, E3. Or we could just take the lead from the English language and call that predicate the. And that's what I've done. So knowledge representation schemes like this that employ extensive reification are called Davidsonian. After the philosopher Donald Davidson, who proposed reifying events, he balked at reifying states, let alone negations of states and events. He would not have treated Chris's tallness as a thing. By contrast, I adopted a position that since I was young and wild, I called ontological promiscuity. Now that I'm older and more domesticated, I would probably call it something like ontological prosperity or ontological comfortable circumstances, or maybe ontological glut. Many balk at the abandonment of ontological scruples like this. No doubt I was influenced by the near solipsism that infected many researchers in the early stages of AI. Our brains could be fooling us just as we often fool computers to test our programs. Yes, there's probably a world out there and it occasionally bites back, but the world is benevolent because we evolved in it. I mean, whenever we breathe, there's almost always oxygen there, and that's no accident. So it doesn't matter very much what we believe. We can believe all sorts of crazy things and be completely ignorant of apparently real and pervasive phenomena. So until recently, until the recent past, we believed in spirits of the dead, and we were entirely ignorant of 98% of the electromagnetic spectrum. In any case, if you're willing to admit the existence of things like physical objects and sets and numbers and possible worlds, what ontological scruples do you have anyway? Why not admit things like John's tallness? So why should we give any credence at all to our intuitions about what exists and what doesn't? Why not simply stipulate that everything that can be talked about exists in some platonic universe of possible individuals, since that makes it so much easier to represent and reason about the content of natural language discourse. So the result of this move and similar reifications to eliminate quantifier scopings is that the logical form is a flat conjunction of existentially quantified propositions with one predication per morpheme. But there's a problem. The representation for John and tall John is tall under this scheme would be that there's a property E1 of John's being tall, and there's a property E3 of property E1 of X being John, and a property E3 of X being tall. John is not tall have both of those properties plus and property E2, which is the negation of property E3. And of course P and Q and R implies P and R. So it looks like John is not tall implies John is tall, which is not a very happy consequence. The problem here is that tall prime E3X does not say that X is tall. It says that E3 is X's being tall, and we're not committed yet about whether this is actually true or not. What we have to do is distinguish between the content of a sentence and the claim of the sentence. So the content of these two sentences is highly overlapping. They both involve some statement about John and about being tall, but the claim is different. The claim in the first sentence is E3, John's tallness. That's what we're saying is true. And the claim in the second is the negation of John's tallness. So we have to distinguish between those two things. Now, how do we determine which of these properties is true and which isn't? I'll illustrate this with the sentence, "The lazy man did not manage to avoid attending the meeting." Step one is to identify the claim, and that is usually the main verb of the sentence, or the highest level adverbial operating on the main verb. So in this case, it would be the not. And then you propagate truth and falsity down through through implicatives. So because not is true, the managing is false. The managing didn't happen. The avoiding didn't happen, and therefore the attending did happen. And then step three is to take kind of the leftover stuff, the grammatically subordinated stuff, and as a courtesy, simply assume that's going to be true. So we'll assume that the entity that attended the meeting was in fact a man and was in fact lazy, and the thing that was being attended was in fact a meeting. So when you make this move, the result is very simple compositional semantics. That is how you build up the meaning of the sentence as a whole from the meanings of the parts. In linguistic semantics, the typical approach is to have every constituent, the meaning of every constituent, be some complex lambda expression. And then when you join two constituents to form a larger constituent, then what you do is apply you use function application. Apply the lambda expression of one, that's the meaning of one entity to whatever expression is the meaning of the other. Thing is, with this flat logical form, the only role for functional application is to identify variables. And so we can forget about the lambdas, we can forget about functional application, and just talk about what variables are identifying. So you get this very simple two-step process. First of all, the lexicon provides predicate argument relations. So I'm going to ignore tense and determiners here. So man tells us there's an x1, there's a property E1 of x1 being a man. Attended tells us there's an event E2 that is the event of x2 attending y2. And meeting tells us there's a y3 and a property E3 of a y3 being a meeting. And the second step is that when we recognize the syntactic structure, what we're recognizing is identity among variables. So when we see that attended a meeting is a verb phrase consisting of a verb and a noun phrase, precisely what that tells us is that y2 equals y3. The thing being attended is the same as the meeting. And when we recognize the whole string as a clause, what we're recognizing is that x1 equals x2. That is, the man and the person attending the meeting are the same. So you get this very simple picture of compositional semantics as identifying variables, where the variables are are provided by the predicate argument structure from the lexicon. Okay, in 1979 and 1980, I had the huge good fortune of to participate in a biweekly discussion group on discourse, alternating between Stanford and Berkeley, consisting of some of the most illustrious scholars of language in the world, including Mike Agar, Dwight Bollinger, even Herb Clark, Chuck Fillmore, Paul Kay, George Lakoff, Jeff Nunberg, Ivan Sog, Dan Slobin, Elizabeth Traugott, Tom Wasow. For me personally, the high point of this meeting, and one of the high points of my entire career, was when the famous sociologist Irving Goffman, who was visiting Berkeley at the time, used my paper, Conversation as Planned Behavior, as a club to beat the sociolinguist John Gumpers over the head with. The Gumpers didn't like the paper, so Goffman defended it. So we in this discussion group, we read and discussed members' papers on interpreting compound nominals, metonymy or deferred reference, denominalized nouns, metaphor, and other phenomena that came to be clustered by linguists under the title Radical Pragmatics. I thought a better name might be run-of-the-mill AI. Around this time, I was concerned with the problem of how we delimit the set of inferences we draw when we understand a text. The answer that seemed most promising was that we draw precisely those inferences that are required to solve this set of problems. But the problem was, what systematicity was there to this set of problems? How would you know if the list was complete? So the approach I took to it was to say, observe that morphemes convey predications, that is, predicates applied to arguments like P of X. That gives you, that leads to three classes of problems. The first is, what is the predicate, P? This subsumes the problem of lexical disambiguation, the problem of interpreting vague predicates like prepositions and the verb, verb have and take and make and so on. Interpreting the implicit relation in compound nominals, and an operation that has been called something like vivification or concretization. So that when I say I went to Tokyo, you interpret it as I flew to Tokyo, which is much more specific than the way I expressed it. The second class of problems are, what is the argument? What is X? And this subsumes the problem of co-reference resolution. And as we saw in the first part of the talk, recognizing syntactic structure is recognizing identity among variables. And so this subsumes syntactic disambiguation as well. And the third class of problems is in what way are the predicate and the argument congruent? Why is it that we can apply this predicate to this kind of argument? And this leads to issues of interpreting metonymy and metaphor. This collection of problems I call local pragmatics. They're the problems that are presented within the scope of single sentences, but they require for their solution the entire discourse, external context, and world knowledge. This term never caught on, I think, because nobody else saw this class as this class of problems as a natural kind. Another issue that I was thinking about during these years was the structure of discourse, in particular the structure that arises out of the coherence relations between discourse segments. In this, I was very much influenced by the work of the linguists Joseph Grimes and Robert Longacre. I began collaborating with the anthropologist Mike Agar at this time, and we called this level of structure local coherence. It's essentially answers the question of what information is conveyed by the adjacency of segments of discourse. I mean, John is leaving means one thing, good means something. When I put them together, John is leaving, good. That means something very much more than that. And that's conveyed by the adjacency of these two segments. In the middle 1970s, Ray Perot and Phil Cohen at the University of Toronto, later to be my colleagues at SRI, and Chip Bruce at BBN, were doing very exciting work analyzing the structure of discourse as arising out of the speaker's or writer's plan, employing formalizations of planning from artificial intelligence. In work with David Evans and work with Mike Agar, I tried to apply these insights to the complexities of ordinary conversation and to ethnographic interviews. Agar and I called this level of structure global coherence. All along in investigating all three of these problems, local pragmatics, local coherence, and global coherence, it was clear that a key role was played by the notions of implicature, accommodation, and abduction. To solve even elementary problems like pronoun co-reference, one had to make assumptions to get a good interpretation of the text, where the only justification for the assumptions was that they did lead to a good interpretation of the text. In the fall of 1987 at SRI, we organized a discussion group on abduction, reading classical papers by C.S. Peirce, recent attempts in AI to use abduction, for example, in medical diagnosis, and contemporary philosophers like Paul Thagard, as well as work by Walensky and Norvig and by Charniak and Goldman at Brown, that seemed to be taking an approach very similar to ours. Among the people in our group were Mark Stickle, a theorem proving expert, Doug Edwards, and the pragmatic scholar Steve Levinson, who was visiting Stanford at the time. We argued about what we were calling identity implicatures and referential implicatures, and about how to distinguish given from new information in discourse, and how to choose the best interpretation of a text. Then late one afternoon in October of 1987, Mark Stickle came into my office to say that he thought he had the answer to all our problems. He described the algorithm for weighted abduction. It struck me immediately as the double helix of computational linguistics, a feeling that has not entirely abandoned me today. First of all, it gave us a characterization of what constituted a interpretation of a stream of discourse. It gave us a clear criterion for what inferences to draw and what not to draw. The interpretation was the most economical explanation for what would make the text true, and an inference was appropriate if and only if it contributed to that explanation. On my way home that night, I began to drive a little more carefully. I saw how one would approach all the problems of local pragmatics and local and global coherence in this framework. And in discussion with Stu Schieber in the next few days, it became apparent how one could integrate syntax smoothly into this framework. A big picture emerged. This is not the big picture. This is an advertisement that I saw in Newsweek in the early 1990s. It's quite obsolete now because Newsweek doesn't exist as a paper magazine, and it's advertising Polaroid cameras, which don't really exist. So we see a boat at the top of a tree by the ocean, and another branch of a tree that's fallen over, and a man looks like he's about to take a picture. So we look at this picture and we try to figure out what's going on, and we see that there's a boat in a tree and there's a branch down. Now it could be that a crane came along and lifted the boat into a tree, and it could be that somebody came along and chopped a branch off of the other tree, and that's why the branch is down. But a better explanation is that there was a storm, because assuming there was a storm that blew the boat into the tree and knocked the branch down, we get a much more economical explanation. We only have to assume one thing, the storm, rather than the crane and the chopping. But of course, there's really a third thing, a third observable that we have to explain, and that's the fact that it's in a magazine. And the reason it's in a magazine is because it's an advertisement. And advertisements are put together by ad agencies, and it could well be that they rented a crane and chopped the branch down in order to achieve this particular scene without waiting for a storm to come along and arrange it for them. So we really have kind of two interpretations here, and both of them are required for properly understanding this picture. One is the informational, what's the situation being described in the picture that we see, and the second is the intentional. Why is it that this picture is being presented to us? What is whoever is presenting this trying to achieve? So the big picture that emerges is this, that the brain is an abduction machine continuously trying to prove the situation it's observing is coherent. And among the observables that it's trying to make sense of are utterances. That is, some speaker I says to some hearer you, some string of words W. Now, what's the explanation of this utterance? Well, usually the best explanation for an utterance is that it's an intentional act intended to convey information. So this particular branch in the tree corresponds to a rule that tells us that if I have a goal, that you adopt some cognitive stance like believe or entertain or think about or imagine, some situation E, where E is the situation conventionally described by the string of words W, then feasibly at least, I will utter to you the string of words W. And then the explanation for this utterance is this, well, it must be that W is a coherent segment of discourse that conveys the situation E, and that I have the goal that you think about that situation. So this gives us on the one side this predicate W being a segment describing situation E. When we come up with a better, more detailed explanation of that, that will be the informational side of our interpretation. When we come up with a better explanation for, a more detailed explanation for the goal and the cognize, that'll be the intentional side of the interpretation. So the goal and cognize lead us to reason about the speaker's plan. That is, what are his goals and beliefs? This is what Agar and I called global coherence. Now, to interpret the segment, the first step is to break it into smaller segments that are related to each other and figure out what that relation is. So the branch here that segment into two segments in a coherence relation captures what Agar and I call local coherence, where you have to figure out, all right, what situation E1 is being described by the string W1, what string E2, what situation E2 is being described by the string E2, and then what's the relation between these two that's being conveyed by their adjacency. And some of the common relations that happen between situations are things like identity or elaboration, similarity, I'm describing two situations that are similar, a ground figure relation or causal relation, or a strong kind of temporal succession that I call occasion, where one situation sets up the occasion for another, and also predicate argument relations. So in the previous example I gave, John is leaving, good. Good is a predicate applied to John is leaving as an argument. So that can happen as well. These are not exactly the relations of rhetorical structure theory, although there's some overlap between them. RST is a mixed bag of informational and intentional relations, both what is conveyed by the adjacency of the segments and why the speaker placed the segments in that particular way. Also, it's often the case that the relation that's conveyed by adjacency is conveyed redundantly and generally with less ambiguity by conjunctions or adverbs or referential expressions. So I might say, John pushed Bill, Bill fell. You assume there's a causal relation. You can make that stronger by saying John pushed Bill, so Bill fell, or consequently Bill fell, or that made Bill fall, and convey that relation redundantly. This coherent structure of the text bottoms out in syntactic interpretable clauses. And as we saw before, syntactic analysis, is just the interpretation of adjacency as predicate-argument relations or identifying variables. All of this bottoms out in the logical form of the text because the best explanation of a morpheme or word is usually that it conveys the corresponding predication. So this logical form leads to reasoning with world knowledge and solves as a byproduct a lot of the local pragmatics problems like coreference and predicate strengthening and so on. I won't go into detailed argument of this, but this was one of the original observations of the interpretation as abduction framework. I'll give a quick example to illustrate how it goes. So we have this sentence due to Graham Hurst, the plane taxied to the terminal. It has three lexically ambiguous words here, plane, taxi, and terminal. A plane can be an airplane, or it can be a wood smoother. A taxi can be for an airplane to move on the ground, or it can be for a person to ride in a cab. A terminal can be an airport terminal or a computer terminal. So we have this ambiguity, and suppose we know all of that, and we know in addition that airports have airplanes and airport terminals associated with them. Then when we try to interpret this, what we try to do is find the least cost explanation, the most economical explanation for this logical form, which is our observable. And what we find is this. Just by assuming that there's an airport and an airplane that we would expect to encounter at an airport is moving on the ground toward the airport terminal we would expect to have at an airport. We get this lowest cost proof, and as a byproduct, the lexically ambiguous words plane, taxi, and terminal are disambiguated because of the axioms that are used in the proof. That is, we use the axiom airplane implies plane rather than wood smoother implies plane, thereby disambiguating that part of the text. So the big picture is this. And we start off trying to interpret the observables in our world as a coherent situation. Among these observables are utterances that are intentional acts by the speaker to convey some information, where that information is conventionally encoded in the string of words. We break that down and discover the coherent structure till we get to the level of a clause. We do the syntactic analysis then until we bottom out in the logical form. We prove the logical form, and that solves the local pragmatics problems for us as a byproduct. Then we get mutual influence among these various parts because we get better explanations by assuming that they share content where possible, giving us the most economical explanation and giving us influence, for example, from the speaker's plans to syntactic disambiguation or lexical disambiguation. Similar work was being done at the same time, as I said, by Charniak and Goldman at Brown and by Norvig and Walensky at Berkeley. So if this framework is so elegant and so all-powerful, why has it not been more widely adopted? And I think there are three problems that have led to this. First, the parsers that we've had have been too inaccurate, leading to an inaccuracy in the generation of logical form. The second problem has been the inefficiency of the engine, the theorem prover that we use for abduction. I mean, it's an exponential process. And the third problem is the lack of an adequate knowledge base. But I think it's each of these three problems there's been some developments in the last few years to ameliorate these problems. First of all, there are now good probabilistic parsers, and many of them have good systems for generating logical form. For example, here at ISI we use the Boxer system, and it produces the ontologically promiscuous logical representation that I was talking about before. Secondly, there has been work by Inoue and Inui in Japan, building on work by Charniak and Santos, on implementing abduction as integer linear programming. When we did this in our system based on Inoue's work, it resulted in a speed up by 2 orders of magnitude in our processing. And the third development has been work on a number of fronts in building up knowledge bases by combining manually constructed axioms, axioms generated automatically from existing resources like WordNet, FrameNet, and by exploitation of various web resources. And a good example of this is Katya's work on combining all of these things, including like FrameNet and WordNet. So moving on, I'll spend the rest of the time talking about my more recent efforts on encoding common sense knowledge. The basic observation about discourse understanding is that we understand discourse so well because we know so much. That means that there are two basic problems in discourse understanding. The first is, how do we encode the common sense knowledge that's required for understanding discourse? And secondly, how do we use this knowledge in the process of understanding discourse? I had a conversation with Eugene Charniak in the early 1990s in which I said I thought the second of these problems was a solved problem, and the answer is abduction. He agreed with me. We both agreed that the real problem now, the most important focus of research now, is the first problem. How do we encode the common sense knowledge that we need? But he despaired that the encoding of he said he despaired of encoding that knowledge manually, and that's why he had reoriented his research towards statistical methods. I disagreed for two reasons. One, I think the kind of knowledge that we need at the very core of the knowledge base for natural language processing can only be done manually by thoughtful people and cannot be done by any automatic methods currently imaginable. And I think there's a systematicity that will make the task more tractable than we might suspect at the outset. So I'll illustrate this with the word range. We would like to have a definition for the word range that would allow us to understand sentences like the scores on the test ranged from 38 to 96 and be able to answer questions like, did anyone get a 96 on the test? Yes. Did anyone get a 54 on the test? Maybe. Did anyone get a 25 on the test? No. But in addition, we'd like this definition of range to work not just for a scale of test scores, but also for things like the timber wolf ranges from Mexico to the Arctic, or his behavior ranged from sullen to downright hostile, or the hepatitis cases range from moderate to severe. So we can capture all of these, the meanings of all of these uses by an axiom like this. So this says that we want to capture the meaning of X ranges from Y to Z, and what that means is that there's a subscale S here, and it's got this subscale S1, and Y is the bottom of the subscale, Z is the top of the subscale. This is 38 to 96 in our previous example. And in X, there's one element that's at Y, and there's an element that's at Z, and all the other elements are somewhere between Y and Z on this subscale S1. Now, it seems to me that it's difficult for me to believe that anytime soon we'll be able to discover rules of this complexity and at the same time rules of this abstraction. I think that we certainly will be able to discover automatically facts such as one has to be married before getting divorced, or houses normally have thermostats. But facts like this definition of range seem to me to require human brains. My formative experience in encoding common sense knowledge came when I was at Yale in the early 1970s and immersed myself in the linguistics literature. Among the papers that struck a chord with me the most were the generative semanticists like Jeffrey Gruber, George Lakoff, Hadge Ross, James Macaulay, and others. They were analyzing the verb kill into cause to become not alive, and the verb move as in X moves Y from Z to W, as X causes a change from Y being at Z to Y being at W. They also speculated on the abstract nature of the at relation as the source for many of the frozen spatial metaphors that pervade language. Generative semantics dropped out of favor rather soon, but I think the fundamental insights were right. To my mind, they failed for two reasons. First, they were doing in tree transformations what they should have been doing in logic, a mistake being repeated today by those working in the so-called natural language inference. Second, they lack a notion of defeasibility, so that when they found examples of X killed Y and X didn't end up not alive, they thought that their theory was refuted. My interests in lexical semantics got put on a back burner for several years. I returned to it in the middle 1980s when Bill Croft, Doug Edwards, Todd Davies, Ken Laws, and I worked on building up a knowledge base. Our goal, which we almost achieved, was to be able to prove as a theorem that wear on the component of an artifact can cause the artifact to fail, because wear is loss of material, and this causes a change of shape, and shape is normally functional in artifacts. We were working at the time on U.S. Navy texts dealing with worn-out air compressors. Then it was back to the back burner until 1999 or 2000, at which time, since which time knowledge encoding has been the principal focus of my research. It's not easy research to get funding for because its payoffs in comparison to building special purpose applications is very long-term. One has to find short-term applications that would help by general knowledge in the next logical domain to attempt. So, for example, the work I did on so-called owl time, or temporal ontology, was funded by the DARPA's DAML Semantic Web project, and work on the vague duration of events with Feng Pan here at ISI was done on a question answering project for ARDA. Work I did with Rutu Mulkarmeda on granular or how-to causality was funded by the DARPA machine reading program. I had several projects that supported research on the structure of events, and the work that I've been doing with Andrew Gordon on common sense psychology has been supported by a number of projects. But a lot of the work just has to be stealth research, that is, research you don't tell your boss about because he'll wonder how you're paying for it. So the problem is, it's not enough to decompose a verb like move into cause, change, at. You have to furthermore say what these predicates cause, change, and at mean. That is, we have to anchor the predicate cause in a theory of causality, the predicate change in a theory of change of state, the predicate at in a theory of composite entities and the figure-ground relation. These aren't primitive predicates, but they're basic predicates whose meanings are constrained by core theories of the abstract phenomena. So you want to anchor these concepts in the core theories. So similarly with the definition of range, we have the word range. We have a core theory of scales that tell us, explicate predicates like scale and less than, and subscale, top, bottom, and at. And then we have the axiom that links this word range with these core theories and tells us what the word range means. So the general enterprise is what might be called deep lexical semantics, where we link words with core theories by means of axioms. We explicate the principal properties of the basic predicates in core theories with sets of axioms constraining the possible interpretations. We express meanings of word senses as logical axioms in terms of these core theories. And this is, I think, a necessarily manual process for the most part. So I'll talk about just 4 of these knowledge encoding efforts very briefly. First of all, composite entities. A composite entity is a thing made of other things. This is about the most basic concept you can think of. It includes things like, books or computers or cars or concerts or university educations or basically anything that you can decompose into smaller elements. It's characterized by a set of components, properties of those components, relations between the components, that is, the structure of the entity, and relations between the whole and entities in the environment, including the function of the entity. And then we can characterize a figure-ground relation that I call at. It takes an external entity, it takes some ground, S, and places some external entity at some location within that ground, where the ground is just a composite entity. And then we can specialize that ground in various ways and get the more precise meanings for at, like spatial location, Pat is at the back of the store, location on a scale, nuance closed at 58, membership in an organization, Pat is now at Google, time of event, at that moment Pat stood up, and so on. And this gives us not only the different meanings of at, it also gives us different meanings of words that are built on at, like range and move. So we can talk about Pat's experience ranges among all of the hot startups in Silicon Valley, or we can talk about moving a meeting from one time to another. This is the basis for most spatial metaphor. In the theory of change of state, we simply have this predicate that says state 1 changes into state 2, where they're different unless there's some possibly intermediate state, and they involve the same entities. So we're talking about the change of state of something. In the theory of causality, the fundamental distinction is between causal complexes and cause. So if I flip a light switch and the light comes on, we say that by flipping the light switch caused the light to come on. But lots of other things had to happen or hold at the same time. So the light couldn't be burnt out, it has to be intact. The wiring has to be intact, the power has to be on in the city, and all sorts of other things that I'm not even aware of. All of these states and events that have to hold in order for the effect to hold are the causal complex. Its chief property is that when all the stuff in the causal complex happens or holds, then the effect happens. And secondly, everything in the causal complex is relevant in the sense that if you toggle one of them, the effect isn't going to happen. So this is a rigorous notion, but in a way it's a kind of a useless notion, because you can never specify everything that has to be true in order for some effect to happen. A more useful notion is cause, but it's defeasible. It's not always true. So when we flip the switch, that we can call that the cause, because that's in a way the active element, or the thing that's not normally true. Causes then are the focus of planning, prediction, explanation, interpreting discourse. They're not the focus of diagnosis, because what happens in diagnosis is we make the cause happen and the effect doesn't happen. Something's gone wrong. So then we have to look at the other stuff in the causal complex to see exactly what went wrong. All right, with these various notions, then we can define words like X lets E happen, to mean it's not the case that X causes E not to happen. The most general sense of go, as in sometimes I go crazy, is a change of state from E1 to E2. X is free of constraint C to do E, means that it's not the case that the constraints cause E not to happen. X holds Y at Z means that X causes there not to be a change from Y being at Z. X releases Y from Z means that there's a change from X holding Y at Z. So we can define all of these very common words in terms of these predicates in our core theories. And once we've done that, then we can answer questions like, suppose I'm told, this is a textual entailment example, suppose I'm told a Filipino hostage in Iraq was released. Is it true or not that the captors let the hostage go free? The problem with establishing this, there's no lexical overlap in these two sentences, or no significant lexical overlap. The problem is that the words let, go, free, and release all carve up the world in different ways. And essentially what we have to do is unpack these words in terms of the axioms we had on the previous slide and kind of repackage them to get the sentence that we want to establish. So in the work on common sense psychology, and this is the last example I'll talk about, it's work with Andrew Gordon, in which we're trying to encode the principal facts of common sense psychology or folk psychology, not how we think, but how we think, sort of what our model of people's thinking is. And we've developed theories of memory, of belief, of envisioning causal chains and other varieties of thinking, perception and the control of the body. And the things that I'll talk about now, very briefly, are goals and plans and emotions. So the idea behind our treatment of goals and plans is kind of the strong AI thesis that people are planning mechanisms. That is, we have goals, we develop plans to achieve these goals, we execute the plans, we monitor the execution. If things go wrong, we modify our plans and execute the new plans. So there are two key properties of goals. The first is, if I have E2 as a goal, and I believe E1 causes E2, then that defeasibly will cause me to adopt E1 as a goal. And the other property is a similar rule for enable. And these rules generate hierarchical plans. So in terms of this, I can define concepts like helping, for example. So the weakest sense of helping is to perform an action in a causal complex for someone's goals. So this would be inadvertent, this would include an inadvertent helping, like McCain helped Obama get elected by picking Palin as his running mate. A stronger sense of helping is when the helper actually has the intention of achieving the helpee's goals. So for example, taking away a drunk friend's car keys helps him survive, even though it's not any part of his plan to survive. And then the strongest sense of helping is to engage in a shared plan, collaborative planning. That's like when you help somebody to carry a sofa where you both know your own roles and you intend to carry out your role. We can define concepts like trying, succeeding, and failing. You try to do E if you have the goal of doing E, and then you begin to execute a plan to achieve E. That is, you engage in some sub-goal of E. To succeed at doing E is to try to do E and have that trying cause E to happen. To fail at E is to try to do E and E doesn't happen. This approach to goals and plans also gives us a handle on functionality. So among many of the most important facts we know about the artifacts in our life are what their function is. And we know this to a very detailed level. So because artifacts can be viewed as plans made concrete. So take a simple thing like a coffee cup. The top level goal we have with a coffee cup is to move coffee. So the way we achieve that is we break it into two sub-goals. First, we'll contain the coffee in the cup, and then we'll move the cup. Now, how are we going to move the cup? Well, we do that by attaching a handle to the cup, and then we move the handle. So you can view this coffee cup as a plan for moving coffee made concrete, or in this case, ceramic. And in terms of this, we can talk about the absolute functionality of the entity, its hypothetical goal, moving coffee, and the relative functionality. So what's the functionality of the handle within the larger object of the coffee cup? So the approach we're taking toward emotions is, the general pattern is for each emotion we try to describe an abstract type of perceived eventualities that trigger the emotion, and then an abstract class of typical responses that the emotion triggers. So all emotions are characterized in terms of what causes them and what they cause. So they mediate between perception and action, like all of cognition. This is basically what you need to know if you're going to fake emotions, which we all no doubt do from time to time. So for example, happiness happens when your goals are being satisfied. If your goals are being satisfied, that means your beliefs in the relevant area are working, and therefore, two of the consequences of being happy should be a higher level of activity, because you might as well do more stuff because you've got the right rules for doing stuff, and you're not open to a change of beliefs because your beliefs are working for you right now. Sadness would be characterized in essentially the opposite way. And the raw emotions like anger, disgust, and fear can be defined in terms of a threat to your goals and your responses depending on the nature of the threat. So for the talk, for the paper that corresponds to this talk, the way I ended was with a prediction about when this kind of enterprise could reach some sort of fruition. For the talk itself, the way I concluded was on a happy note, that with this award I've more than satisfied my professional goals, therefore I'm happy, so I must have done something right. I'm going to party, no one can talk me out of it.
Well, thank you, Jerry, very much, and once again, congratulations on your Lifetime Achievement Award. So we're going to have around 10 minutes for questions, and after that, please stay, because there's going to be like a small receptions with refreshment. So, hi, thank you. Well, I guess I learned a lot. Thank you during this talk. I had a question. You mentioned that in interpretation part, our brains find or look for the most economical explanation, and that's the interpretation, and that's the right one. So is there evidence? This kind of suggests to me that there is a search going on. So is there evidence that the brain is searching around for possible solutions? And in that case, I mean, if as the sentences get more and more complex, does it take them longer to find the most economical solution? Is this an actual search procedure that the brain does?
Yeah, I don't know. I mean, I can tell you, I personally think of these proof graphs as little neurons, reaching out, dendrites and so on, sending signals from one to another. And there's been the researcher Lokendra Shastri has developed a neural net model that kind of does the kind of logical deduction, abduction by this kind of searching by kind of searching through this and then killing off the losers and zeroing in on a single representation. But I don't know, of any detailed results on something like this, and I'm not sure what the prediction would be.
Well, one of the predictions would be that it takes.
Well, I don't know.
Well, it will take longer for people to comprehend more complex, longer sentences with more multi-ambiguous words in them.
Well, except that the interpretation of the early part of the sentence might narrow down the search in the later parts.
That's true.
So I'm not sure that's really the case. Billy.
Question? Okay, Billy.
So, thank you for a fantastic presentation. Very, very cool. My question question is concerned with the domain of discourse that you're kind of inhabiting and working within. By working in common sense reasoning, you're kind of scoping the entire universe in a way. It's like whatever your brain is capable of thinking about, you're trying to find the underlying reasons for that. But obviously we have domains of knowledge, and people think and work in specialized domains. So how would one take these very general concepts that you're talking about here and maybe refine them and focus on using the same kind of approach in a more specialized subdomain, such as neuroscience or ethics or something like that?
When you look at any technical domain, you think, oh, there's going to be a lot of technical vocabulary here, and there is, but it amounts to about 30% generally. And the other 70% is just ordinary language, words like have and in and range and move and so on. So you never, I think in the bio literature, it may be more than 30% technical. It's probably more like 60 or 70% technical, but there's still a lot of just ordinary English there that forms the framework that all the rest of the stuff is built on. And so what I'm trying to do in the common sense knowledge is try to figure out what those very basic things are that pervade everything. Things like, the really abstract things like composite entities and figure ground and so on.
Final question? Okay.
Yeah, this was a lot of fun. This sort of appeal is so elegant, and what I wonder about is, you're a very brainy individual, and if my logic is sort of screwed up, and my common sense is not really common sense. Are there a lot of, is there evidence that most people do in fact sort of share a common sense that can be described in logic, or are sort of enough individuals have sort of their own weird logic that?
Well, the logic is not particularly deep. It's basically predicates applied to arguments, and it's pretty hard to imagine how higher mammals can get by without something like that. You have conjunction. You recognize contradictions. You can do modus ponens. You can, from P and P implies Q, you can figure out Q. But there's nothing exotic there. There's 4 or 5 properties of the logic that it's just obvious that people do without effort. The content of the common sense theories might be very different. If I think that Martians are talking to me, then, obviously the content of my theory of the world is somewhat different, and certainly various ideologies, cause you to interpret things in very different ways. But the world, for the physical world, the constraints of the physical world on you are so much that there's a real limit to what kind of theories you could have and still survive. And as far as the social world goes, the more abstract things, it doesn't matter very much what you believe. You're still going to get by because that's the kind of, we've evolved in this environment.
Well, let's congratulate Jerry one more time. And feel free to talk to Jerry during reception time.